Hello, in this session we will discuss a quantum mechanical particle moving in one-dimensional box. Now the understanding of this problem, that is the quantum mechanical particle confined in a one-dimensional box, helps in solving many other complex problems. The best crude application of this one-dimensional box problem is to understand the linear pi conjugated systems. For example, this is a linear pi conjugated molecule. This is 135 hexatriene. So for this kind of molecules, the electronic transition, if we study the electronic transition, those electronic transition can be studied through one-dimensional box problems, and the solution of those electronic transition or energy values will essentially give us essentially inform us the length of the molecule. So this is a crude application of this one-dimensional box problem. Further, this understanding of one-dimensional box problem helps in understanding the understanding of real world problems such as tunneling of electron, that is traveling of electron in a forbidden zone, and that concept is specially used in scanning tunneling microscope, and those microscopes are very helpful in imaging applications, particularly in material chemistry. And further, this understanding of particle in one-dimensional box helps in understanding the certain chemical reaction, particularly the hydrogen transfer chemical reactions. Further, we can also understand the conduction of electron in metallic crystals by with the preliminary understanding of particle in one-dimensional box problem. So as I said, it will be a one-dimensional box. We'll consider a model for that. We have a box, one-dimensional box, and by default the dimension is x dimension, and the length varies from 0 to L, and there are three regions: before the box and after the box and inside the box. It is assumed that the wall of the box is the height of the wall of the box is such that the potential energy to cross the barrier or to cross the wall is infinite. Means suppose the particle confined in this region, in the middle region, wants to cross the box, it has to attain infinite amount of potential energy, then only it can cross the box from before the box and after the box. But essentially that is not possible, because infinite amount of potential energy, the particle cannot gain infinite amount of potential energy. So particle is essentially confined in region 2, and it is absent in region 3 and region 1. So this the above one-dimensional box example, the potential energy does not change with time. The potential energy in the region 2 does not change with time, and we will consider that in the region 2 the potential energy is 0, that is from 0 to L. When x is between 0 to L, the potential energy is 0, and before 0 and after L the potential energy is infinite. And therefore we can find stationary states. When the potential energy in the region 2 is not at all changing with respect to time, the solution of the wave function or solution of the state functions will give us stationary states, that is the states which does not vary with respect to time. To find out stationary states, we have to solve time independent Schrodinger equation. TISC means time independent Schrodinger equation, and we are considering a one-dimensional system, so our variables will be only with respect to x-axis. So if I write a time independent Schrodinger equation for one-dimensional system, the equation goes like minus h bar square over 2m d square over dx square plus vx psi x is equal to E psi x. Now the first term is the kinetic energy part, the second term Vx is the potential energy part, psi x is the wave function, E is the eigenvalue of energy. E is eigenvalue of energy, and psi x is again the same state function or wave function. We'll consider all the regions, that is region 1 and 3, that is before and after the box, and region 2, that is inside the box. First we will consider region 1 and 3. In the region 1 and 3, the potential energy is infinite. So when the potential energy becomes infinite, the kinetic energy becomes 0. So my time independent Schrodinger equation will be reduced to Vx psi x is equal to E psi x. So kinetic energy part is 0, so the time independent Schrodinger equation is Vx psi x is equal to E psi x. Now we are considering the potential energy is infinite in region 1 and 3, so the left hand side is approaching towards infinite, but the right hand side is not infinite. Energy cannot have infinite values, so there must be some finite values of infinite energy. So this is a contradictory condition, means the left hand side is approaching towards infinite because potential energy is infinite infinite in region 1 and 3, whereas energy is finite. So how to solve this contradiction? The only way this contradiction can be solved is we have to take the situation that the wave function or psi x is equal to 0 for region 1 and 3. Psi x is equal to 0 for region 1 and 3 means the wave function of the particle is 0 in the region 1 and 3, means the particle is non-existent in region 1 and 3. Now this helps us reaching a condition called special condition called boundary condition, that is psi 0 and psi l, means at the boundary the wave function becomes 0. The wave function is only positive when or the wave function has some certain values only within the box, that is in region 2, and beyond region 2 the wave function is non-existent. So this equation 1 is called boundary condition, and this boundary condition will be very helpful to solve the behavior of the particle in the region 2. So we will go to the region 2 now. In region 2 the potential energy is constant, and we will take that constant as 0. So now we will solve the time independent Schrodinger equation for region 2. The potential energy is 0. So in the Hamiltonian operator or the energy operator, we have only the kinetic energy part, that is minus s bar square over 2m d square over dx square multiplied with the state function or wave function gives rise to energy, and multiplied with the same state function or wave function. I can rearrange that, simple rearrange. I'll get an expression like this. In the RHS side of the expression we have 2me over h square. All these terms are constant. I'll replace all the terms as k square. So my k square is equal to 2me over h bar square. So if I do that, I'll get a second order differential equation, and that is d square psi x over dx square is equal to minus k square psi x. So what is the solution of this differential equation? The solution of this differential equation, there are two independent solutions, and they are a sin kx and b cos kx. Both these solutions will satisfy this second order differential equation. So what will be the total solution? We will take a linear combination of both the independent solution, and get a most general solution. So the most general solution of this second order differential equation or the time independent Schrodinger wave equation is psi x is equal to a sin kx plus b cos kx. Now right away I have assumed that the solutions are a sin kx and b cos kx, and I have taken a linear combination to get the most general solution for this particle in the region 2, or the solution of time independent Schrodinger wave equation for the particle in region 2. Now I'll quickly go through the detailed solution, and the detailed solution is optional in nature. So still we will quickly go through the detailed solution of this second order differential equation. I have rewritten the second order differential equation as d square psi x over dx square plus k square psi x is equal to 0. What is my k square? My k square is 2me over h bar square. Now experience shows that every solution to a linear differential equation with constant coefficient, the coefficient is constant here. What is the coefficient value? 2me over h bar square. All are constants here. So for constant coefficient whose right hand side is equal to 0, for this kind of solution, for this kind of differential equation, the solution lies in the form psi x is equal to e to the power alpha x. Now what is alpha? Alpha is a constant in the exponential form. So if I substitute this solution in the equation 1, I'll get my value as alpha square plus k square psi x is equal to 0. This will be the solution of this ordinary second order ordinary differential equation. So in this solution the RHS side is 0. So there are two possibilities, either psi x is equal to 0 or alpha square plus k square is equal to 0. Now psi x cannot be 0 because the wave function is 0, means this is a trivial solution, means the particle is non-existent within region 2. But we are saying that particle exists within region 2, so psi x cannot be 0. That means alpha square plus k square is equal to 0. That further gives alpha is equal to plus k or alpha is equal to minus k. So if I put alpha is equal to plus k, my solution will be e to the power kx. Another solution will be e to the power minus kx. So there are two possible solutions are there, e to the power kx and e to the power minus kx. Then to get a most general solution, I will take a linear combination, and in the linear combination C1 and C2 are constant coefficients. the C1 and C2 are constant coefficients of the linear combination. So my solution of the ordinary differential equation becomes psi x is equal to C1 e to the power kx, C2 e to the power minus kx. According to Euler's rule, there is a standard form for the exponential, that is if there is a exponential of the form e to the power I theta, I can write cos theta, I can write that expression in trigonometric form as cos theta plus I sin theta, or e to the power minus I theta is cos theta minus I sin theta. So I will apply this Euler's rule to my equation 2, that is the to the solution of this ordinary differential equation. Then for e to the power kx, if I expand in terms of Euler's rule, I will write cos kx plus I sin kx. Similarly, e to the power minus kx can be expanded as cos kx minus I sin kx. If I rearrange, I will get C1 C2 cos kx plus I C1 minus I C2 sin kx. Again, C1 and C2 are constant coefficients. So for C1 and C2, I'll assume that C1 and C2 is another constant which is equal to B, and I C1 minus I C2 is another constant which is equal to A. So my solution becomes, in trigonometric form, my solution becomes psi x is equal to B cos x plus A sin x. This is what we have obtained here in equation 2. So now our solution for a particular region is psi sin x plus B cos kx. Now to this solution we will apply the boundary conditions. What are the boundary conditions? The boundary conditions are the wave function is 0 at both the boundaries. The boundaries are x is equal to 0 and x is equal to L. So psi 0 is 0, psi L is equal to 0. What is my solution? My solution was A sin kx plus B cos kx. I will apply the first condition, that is x is equal to 0. There are two boundary conditions, x is equal to 0 and x is equal to L. The first boundary condition, if I apply x is equal to 0, psi 0 is equal to A sin 0, kx is equal to 0. So psi A sin 0, B cos 0. Cos 0 is 1, sin 0 is 0, cos 0 is 1. So I will get B, only B is equal to 0. According to boundary condition, psi 0 is 0. So that means my B value will be 0. So for the first boundary condition, that is x is equal to 0, if I solve the solution, if I apply the boundary condition to the solution, I am getting B is equal to 0. B is equal to 0. Now I will apply the second boundary condition, that is x is equal to L. So when I apply x is equal to L, what was my solution? A sin kx plus B cos kx. So x will be replaced by L. So A sin kl plus B cos kl. Again, that wave function at x is equal to L is 0. From the first boundary condition, we have obtained B is 0. So the second part becomes 0. The second part becomes 0. Now A sin kl is equal to 0. A sin kl is equal to 0. This can only be obtained under two circumstances. One is either A is equal to 0 or KL is equal to 0. But A cannot be 0. If A is also 0, then this wave function will not be existing, because from the first boundary condition we have obtained B is equal to 0. So B is equal to 0, A is equal to 0, that is not possible. So A must have some values, so A cannot be 0. Then there is only one option left, that is KL is equal to 0, means sin KL is equal to 0. When sin KL is equal to 0, so therefore we have only one option left, that is KL is equal to 0, means sin KL is equal to 0. When sin KL is equal to 0, when KL is equal to n pi, when KL becomes n pi, then only sin n pi is equal to 0. Now when sin n pi is equal to 0, when n have values 1, 2, 3 and all those values, then only sin KL will be equal to 0. So I am stating that KL is equal to n pi. Now this is an important condition also. We will discuss the consequence of this important outcome from this boundary condition. So basically we are imposing boundary conditions to the solutions of time independent Schrodinger equation for the particle in region 2, and from the imposition of boundary condition we are getting an important parameter or important criteria, and that important criteria is KL is equal to n pi, and n value varies from 1 to 3 up to this continues. N values are integer. N cannot be 0. If n is equal to 0, again the wave function will vanish and that will be a trivial solution. So n cannot be 0. N cannot be 0, and because if n is equal to 0, sin 0 becomes 0 and this wave function will be vanishing. So that's why n cannot be 0, and n can only have values from 1 to 1 2 3 and like that. So I have shown that k square is equal to 2me over h bar square. We have discussed this already. Now if I rearrange, I'll get an expression for energy, and that energy expression goes like n square h square by 8 ml square. So this is the energy expression that I have obtained from k square value, and k I have substituted k as n pi over L, because KL is equal to n pi. So here I have substituted k as n pi over L. So ultimately I am getting an energy expression which is n square h square is over 8 ml square, and n values varies from 1 2 3 like that. Here please mark the difference between h bar square and h square. This is only h square, and here in the previous expression this is h bar square. Therefore the solution of energy we are getting from k square. We will also obtain an energy expression for energy, the same expression for energy, by solving the eigenvalue eigenfunction problem later in this in the same session. We'll obtain an energy expression for energy by solving the eigenvalue eigenfunction problem. So now we'll continue with the wave function. Our wave function is what? A sin kx, b cos kx, but b is 0. After applying the first boundary condition, we have obtained b is equal to 0. So the wave function becomes only a sin kx. Now what is k? K is equal to n pi over L. So the wave function is a sin n pi over L x. So this is the wave function, and when this wave function is valid in the region x, when x is in the in between the limit, that is 0 to L, when x is less than 0 or greater than L, then this wave function is not applicable. So our wave function for the quantum mechanical particle in the region 2 is a sin n pi over L x. Now this is the wave function is 0 when the x is less than 0 or greater than L. Now the requirement that when we have substituted KL is equal to n pi, we are getting important consequences, that the energy spectrum is continuous. Here in energy value, we are the energy value expression for energy value, we are getting n square h square by 8 ml square. So the energy depends upon n. When n value will increase, the energy will also increase. So we are getting discreteness. We are getting discreteness in energy. So for the quantum mechanical particle in the one-dimensional box, the energy value is not continuous, rather discrete. And from which condition we are getting that? By applying the boundary condition, and by imposing the condition that KL is equal to n pi, then only we are getting that the discreteness of energy values. Therefore infinite number of eigenfunctions of the total energy operator. So we can get many number of energy values for the particle in the box, especially in the region 2, because if n value starts from 1 and it goes up to infinity, so there are many energy values are possible, and they are called all eigen states. Now we'll discuss the wave function is given as the wave function of the particle in the region 2 is given as a sin n pi over L x. So we'll determine this a value. This is a is a constant, and that constant is called normalization constant, and that normalization constant will determine. To determine the normalization constant, we have to apply normalization condition. What is the normalization condition? Psi star x, psi x integrated over whole space is equal to 0. Means what does this mean? This means that there is a certain probability that the particle will be found within the region considered. And what will be the region considered in our one-dimensional box problem? The region we have considered is 0 to L. We are saying that in the region 2, or from the length starting from 0 to L, the particle is found somewhere in the region. So I'll apply the limit from 0 to L and apply the normalization condition. So, and I will substitute my wave function. What is the wave function? A sin n pi over L x. So I'll take the complex conjugate first, then the wave function, then dx is equal to 0. Then since there is no complex part, we can directly say a square is a constant. It will come out of the integration, and within the integration I will be having sin square n pi x over L dx is equal to 1. How to solve this trigonometric function? There is a identity, trigonometric identity. I'll use that trigonometric identity, and the identity goes like, if sine square theta is there, then I can write 1 minus cos 2 theta over 2. I'll use this trigonometric identity within this integration and solve the integration, and if I do away with the solution, ultimately I will get a is equal to root over of 2 over L. So my constant a is becoming root over of 2 over L. This is the normalization constant. Now if I substitute my normalization constant in my wave function for the particle in region 2, or for the particle within the box, then how the wave function will look like? The wave function will look like psi nx is equal to root over of 2 over L sine n pi x over L. This n is variable, n varies from 1, 2, 3 like that. So for different values of n, I'll get different wave functions, or different state functions are possible. It is important to note psi n is a function of x but depends upon quantum number n. This quantum number is a new concept that we have obtained by imposing the boundary condition on the time independent Schrodinger equation for the particle within the box. For the particle within the box, when we impose the boundary condition, then only we are getting this n, this integer n, and that integer is called a quantum number. So upon solving those boundary conditions, or upon imposing those boundary conditions on the time independent Schrodinger wave equation, we are able to get this quantum number. And when this n value varies, there will be different wave functions or state functions for the particle. The same particle can have different states possible. Like for n is equal to 1, it can be having one type of wave function. For n is equal to 2, it can be having different type of wave functions. We will see these functions and the nature of those wave functions immediately. Just now we'll see how those wave functions look for different values of n, and what are the consequences of that. Now, as I said before, we have obtained an energy expression from the k values, and the energy expression goes like n square s square by 8 ml square. But we can also obtain the energy expression by solving the eigenvalue problem. For the particle in the region 2, the potential energy is 0 and there is only kinetic energy is there. Then the time independent Schrodinger wave equation becomes minus s bar square over 2m dou square psi over dx square is equal to E psi. Now E is the eigenvalue and psi is the eigenfunction. Now from previous solutions we know that the wave eigenfunction is root over of 2 over L sine n pi x over L. So when n varies, the eigenfunction varies. Now I'll substitute this eigenfunction in my time independent Schrodinger equation. So if I substitute and if I regenerate that in the right hand side, if I get that wave function again, get back that equation or this wave function, then the constant associated with this wave function will be called energy. So if I'll do that, I'll substitute the psi value. I'll put this psi value, this wave function in the left hand side. So if I do that, then I have to take a double derivative with respect to x, and if I do that, if I solve this function if I take the double derivative of this function, this sine function, first I will get a cos function, then if I take another derivative, I'll get a sine function. Means you see, I am getting the same wave function, I am getting back the same starting wave function. You see the RHS, I am getting the same starting wave function. So the constant associated with the wave function will be my energy, because I am using the energy operator. This minus h bar square over 2m dou square by dou x square is the energy operator. So in the RHS side, the eigenvalue will be the energy eigenvalue, and there is no potential energy here, only kinetic energy part is there, because in the region 2 the potential energy of the particle is 0. So my energy expression becomes, so this constant term is my energy expression. My energy expression becomes h bar square over 2m n pi over L square. So if I rearrange, again mark the difference between h square and h bar square, I'll get h bar is equal to h over 2 pi. So if I substitute that, then I'll get an expression for energy which looks like n square h square over 8 ml square. Now the energy depends upon the integer n, and this integer n is again called the quantum number. As the quantum number increases, the energy of the particle in different states will increase. And how the states will be defined, the eigenfunction, through the eigenfunction, the expression for energy eigenfunction is psi n x is equal to root over of 2 over L sin n pi x over L. Here we have obtained that. So this is the energy. Now how those energy values look, how the graphical representation, we'll see. Now the first graph shows the wave function with respect to position. The first energy value will be n square h square 8 ml square. For the first state, n will be 1. N cannot be 0 because that will give rise to a trivial solution we have discussed. So for n is equal to 1, the energy value is h square over 8 ml square. So if I plot the wave function, what will be the wave function? The wave function will be 2 over L sin n pi x over L. So if I substitute n is equal to 1 and I take the length of the box as 1 unit, if I do that, then I'll get my wave function that looks like this kind of graph. So at the boundary, the wave function is non-existent, and at the middle of the box, the wave function have highest amplitude. So this is for first state. And the right hand plot, the right hand side of the graph shows probability density versus position. The left hand side of the graph shows wave function versus position, and the right hand side shows probability density versus position. We've studied what is probability density. This graph is only psi x, the left hand side, and what is probability density? It is psi star x. Since the wave function does not contain any complex part, the probability I can directly write psi star x. So if I take psi star x, then the probability that the particle will be found at the center of the box is higher. This is for first state, first eigenstate. For the second eigenstate, the n value becomes 2. If I plot the function, how the function will look like? The function will look like root over of 2 over L sin 2 pi x over L. For instead of n, I am writing 2. The function will look like it will have a positive part and there is a negative part, and in the center of the box the function is 0. The wave function is 0, means at the center of the box, what is the probability of finding the particle at the center of the box? 0. For the first eigenstate, the probability of finding the particle at the center of the box is maximum. For the second eigenstate, the probability of finding the particle at the center of the box is 0. And how the probability density is obtained? The probability density is nothing but psi 2 x square. If I take square of that function, the state function, I'll get probability density. Similarly, for n is equal to 3, I'll get a wave which looks like this, means there are 2 nodes. For n is equal to 3 state, there are 2 nodes, means at 2 positions the probability of finding the particle will be 0. And what are the 2 positions? The 2 positions are x is equal to L by 3 and x is equal to 2L by 3, means this position. The first position is L by 3, the second position is 2L by 3. The total length is L. So at L by 3 and at 2L by 3 or 2L over 3, the probability of finding the particle will be 0. Suppose I consider n is equal to 100. So the wave function will look like I cannot distinguish where my particle will be found and where my particle will not be found. There is both positive and negative part, amplitude is there. If I take probability density, then only positive parts are there, and I precisely cannot say where my particle will be found. My particle can be found at any place starting from 0 to L. But for first eigenstate, my particle is found at the center of the box. For the second eigenstate, it is found at the probability of finding the particle at the center of the box is 0. Similarly, for the third eigenstate, the probability of finding the particle at L over 3 and 2L over 3 is 0. But when n value becomes large, for this case it is 100, I cannot say where my particle is found and where my particle is not found. Means at every position there is a probability that the particle can be present there. So as n increases to larger values, the probability that particle can be found anywhere between 0 to L increases. I cannot precisely say where I will get my particle and where I will not get my particle. To understand the wave functions, these are wave functions, and the second column of graphs are the probability function, that is the square of the wave function. The first wave function is, to understand the wave function, the first wave function is root over of 2 over L sine n pi x over L. For first eigenstate, the n is equal to 1. So when this wave function will vanish, when I substitute x is equal to L by 2, then only the wave function will vanish. So sorry, when I substitute L by 2, x is equal to L by 2, I'll get sine, if I substitute L over 2, I'll get sine 90, and sine 90 is maximum. So at L by 2, that is at middle of the box, the probability will be maximum. Similarly, for the second eigenstate, if I substitute x is equal to L by 2, if I substitute L is equal to L, x is equal to L over 2, then what will happen? I'll get sine pi. Sine pi is 0, means the wave function is vanishing. The wave function will vanish at L by 2. So this is peculiar thing. And for the third state also, if I substitute x is equal to L over 3 and x is equal to 2L over 3, then I'll get my wave function will be vanishing. I'll be getting pi values, means for L by 3 I'll get sine pi, and for 2L over 3 I'll get sine 2 pi, and for both the cases the wave function will vanish at x is equal to L by 3 and x is equal to 2L over 3. So what are the conclusions that we obtained from understanding these graphs? That is the wave function with respect to position and probability density with respect to position. Then to summarize those conclusions, I can say the number of nodes or the position where the particle will be not found is equal to n over 1. Means the eigenstate minus 1. If it is the third eigenstate, then the number of nodes will be 2. If it is a 10th eigenstate, the number of nodes or number of positions where particle will not be found is 9. The number of nodes is equal to n over 2. As the value of n increases, the quantum mechanical result matches with classical result. Classical result says the particle can be found anywhere between 0 to L, but quantum mechanics says when n value is less, quantum mechanical result says we can precisely say where the particle will be found. But when n increases, we cannot say where the particle will be found. So as the value of n increases, the quantum mechanical result matches with classical results. Again, this is an important observation, and this observation is called the correspondence principle. We will also discuss what is correspondence principle. Means as the quantum number increases, or as the value of n increases, the quantum mechanical results matches with classical result. What is classical result? Classical result says that the particle it is possible that we can define the particle at any position. Means the particle can be found out at any position from 0 to L. So when n values increases, the quantum mechanical result matches with the classical mechanical result. Now why cannot a quantum mechanical particle just sit without moving? Means here according to quantum mechanics, the particle cannot sit ideally, it has to move. Means it has to move, means it cannot sit ideally, means delta x, means the change in position, uncertainty in position is equal to 0. If uncertainty in position is equal to 0, then if the particle is not moving then and sitting ideally, then delta x is equal to 0. If uncertainty in position is 0, then uncertainty in momentum will be also 0 and will be infinite actually. So there is a concept called Hazenbox uncertainty principle, and according to that principle, if uncertainty in position is 0, then uncertainty in momentum will become infinite. So this is not 0, this is infinite, and that uncertainty in momentum cannot be infinite. So that's why the quantum mechanical particle cannot just sit without moving, it has to move, and it cannot sit ideally. Then there are few other important points. The spacing between successive energy level increases as the value of n increases, because energy depends upon n as square. So when n is equal to 2 and n is equal to 1, there is 4-fold increase in energy value. Similarly, when there is n is equal to 3 and n is equal to 1, there is 9-fold increase in energy value. So as the n value increases, the spacing between successive energy level increases. Then the second point of importance is the quantization condition arises from boundary conditions. We have discussed it, means this quantization condition, this means the energy levels are not continuous, rather they are discrete. So this discreteness condition arises from the imposition of boundary condition to time independent Schrodinger wave equation. We have discussed this already. Then the third point of importance is the wave function of a particle in one-dimensional box behave as standing wave, because the particle is confined. It cannot go beyond below 0 and above L, means it is confined in the region 0 to L. So such kind of behavior, such kind of confinement gives rise to standing waves. And for standing waves, the energy of a state is independent of time. So for the energy of the particle is independent of time. But for traveling wave, when the particle is not confined and when it is traveling freely, the energy is dependent upon time. And for the nodes of standing wave are also fixed, but the nodes of traveling wave are not fixed. So essentially it says that the particle in one-dimensional box behaves as standing wave. So therefore boundary condition in equation 2 cannot be applied to traveling waves, but we are not considering the traveling wave here. We are considering only the standing wave. Now what is the correspondence principle? As I said, when the quantum number increases or when n value approaches to higher numbers or higher integers, then the wave function becomes equally distributed over all space. From 0 to L, the wave function becomes equally distributed. What does that mean? That physical significance of this equally distribution means the particle can be found anywhere between 0 to L, and that is the classical result. Classical mechanics also says within a box, and the particle can be found anywhere from 0 to L. And when the n value, the quantum number, increases to large number, our quantum mechanical results also matches with classical mechanical result. So that difference between quantum and classical result disappear as n becomes large. This is a general result known as correspondence principle. So with this we'll stop here. In the next session we'll discuss how we can use the quantum mechanical postulate to understand the particle in one-dimensional box in a better way. Thank you.